folks sticking around. I know it's been a long day. So this is a workshop. Happy to keep it informal. If you have questions, feel free to interrupt me. We can take it sort of easy here, not be super formal. And, yeah, I did try to put something together here. So this is a workshop presentation. I haven't actually given this before, so let's see how it goes. And yeah, like Eric said, really what I'd like to see is these new emerging privacy-preserving computation techniques like homomorphic encryption and multi-party computation be practical in some sense in the next 5 to 10 years. And what I'll talk about today is some of my lab's efforts to sort of realize that reality. So yeah, if you think about it, security and privacy are really emerging as first-order design constraints in one way or another. So on the security frontier, right, there's new attacks every day, and these are things perhaps in this community that we're most familiar with, like Spectre and Meltdown, but it ranges all the way up to software and really low-level hardware attacks as well. And on the privacy front, we're also seeing people starting to actually care how their data is being used and who can see it. So with GDPR, these are offering new laws and protections over how companies can use people's data. And we also saw Facebook get hit with a record penalty about 4 or 5 years ago, $5 billion for abusing users' data. And to me, what I see is a fundamental problem. What we're trying to do is build security and privacy primitives on fundamentally non-secure technologies, like a lot of the software we deploy today, or the computers that we run all of our code on. So fortunately, within the last 10 years or so, there's been a sort of breakthrough in means of how we can do computation. And this is what's so-called privacy-preserving computation, or PPCs. These are new paradigms of computation that take place using cryptographic primitives to allow computation directly on encrypted data. So this is stuff like homomorphic encryption or multi-party computation, where you can extend the security guarantees of data from just transmitting encrypted data into the actual computation itself, so the person, the cloud, computing on the data never actually sees it. So it's quite remarkable. The problem is all known cryptographic or information theoretic, if you want to get specific, solutions are fundamentally not practical. So we've actually implemented these things in our lab, benchmarked them and run them, and what we consistently find is that for a single inference, just running one inference on like a ResNet 18, a pretty small model, takes on the order of tens of minutes. So we need full stack solutions to sort of overcome these bottlenecks. So what do I mean by privacy preserving inference? And we're going to focus on machine learning for this talk, but PPCs could be applied more generally to a wide range of problems. So let's say some client, some user has some private data, say some medical data, but they want to outsource it to have some computation performed on it. What they're going to do is encrypt their data X, send it off to the server, say the server is a hospital that has some high performance machine learning model, and then the server is going to be able to directly compute the inference on the encrypted data, send the encrypted result back so the hospital wouldn't even see the result, and then only the end client could decrypt it and get the result of the inference. And one really important thing I want to mention here is that these protocols, these two-party protocols between the client and the server, they don't only protect the input data, they also protect the model, right? So we don't want to just ship the model to the client. That also has problems. The server doesn't want to give up their IP. So it's protecting both parties. So it's pretty powerful. And for this talk, we'll mostly focus on two primitives. The first one is homomorphic encryption. That's basically what's been described here. And the second one is garbled circuits. So we can talk about those over the next couple slides for a bit of background.
Clarification question on the previous slide. When you go back with the encrypted Y, I think there's some implicit assumption that that's relatively simple. A person could look at it on their laptop and understand the results. Are there any cases where it's that itself could be a terabyte of data and it's not really fit for human consumption in the way to naturally process it would be in the cloud, which puts you back in the thing needs to understand it would be
Yeah, so then hopefully the client, so usually when we think about these things, we think about the client being a smartphone or perhaps a laptop. But in that case, a different setup would be one data center to another, or you would have to have some server resource. It doesn't solve that problem. So then what you have to do is you would have to go, what you could do is you could get your result, say, okay, this is too big for me. Now I need to outsource more computation. I need to re-encrypt it and send it back out to the cloud to do more stuff. And
but I guess the assumption at the end is you come back with an answer like, yes, this is a problem. No, it's not. It's something that a human can easily deal with in any computing device.
For now, most of the applications, that's what we're looking at. Yes, no, classification, analytic, distilled, terse type answers. Yep, definitely. Okay, so homomorphic encryption. This is for secured outsourced computation, which is what we were just discussing. So client has some value, call it X. Server, in this case, would have some weights or a matrix, W. The client's going to encrypt it, send it over. The server does the computation, gets the encrypted result out, sends it back. And what homomorphic encryption is really good at is a couple different things. It's good at processing linear transformations. So anything that's an addition or a multiplication, it's going to work really well. And it works well when you have really long sets of data. So things that are vectorizable and really long vectors. So this is sort of a natural fit for the linear layers of machine learning. Things like fully connected layers, convolutions, all that's going to work really well with HE. The other benefit, there's not a lot of communication or storage requirements. It's pretty much just a computational load, but that computational load is extreme. Another technology that fewer folks have heard of, but is actually super cool and important, are these things called garbled circuits. So garbled circuits are a true form of multi-party computation. And I'll walk you through at a high level how they work. But basically, the first thing you have to do is take any function, say your C code or whatever you want to compute, and you have to boil it down to a net list, basically Boolean gates of ands and XORs. Okay, so once you have your function represented, you're first going to send it to the party that's called the garbler. That's typically the server. And what they're going to do is generate a bunch of pre-computes. Basically, we call them tables. They're computing, you can think of it as like this really big lookup table for every single gate. And they have to go and do that for each gate in the entire network. So they basically have to process the entire circuit. Then it takes all of those pre-computes and sends them over to the client, who we call the evaluator. And as the actual inputs that you want to compute on privately arrive, the client's going to use those pre-computes and basically evaluate, using all those tables that the garbler generated, the function. Then we get an encrypted output for the circuit, we send it back, and we can decrypt it, and the server can share it with the client or not, depending on the protocol. But the important distinction here is that in garbled circuits and a multi-party computation, both parties, the client and the server, actually have to run the computation, whereas with homomorphic encryption, it's only the server, the evaluator. So the benefits of garbled circuits are that because we're using a Boolean circuit representation of a function, we can evaluate anything. Like literally any function can be computed in garbled circuits, whereas with HE, we're very limited. The drawback is that the computation is really expensive. We'll get into that a little later. The communication is really expensive. You have to send a lot of data back and forth. And that also ends up putting pressure on the storage system, which we'll see some data on later. So yeah, garbled circuits, huge potential, but a lot of bottlenecks to overcome.
I assume, I'm sorry, I don't know garbled circuits. It's all combinatorial logic, so anytime there's no states, and that's one reason for all the communications. Because
yeah, even if you do have a sequential circuit, you can't reuse those tables. So you would have to generate unique you would have to generate unique things for every re-entry of the gate, which is a huge problem. So there have been fully unrolling loop is a good way to think about it. There have been papers, these tables are, we'll see some data, they're nasty. So there has been some papers to look at reusing them, like across, say, AND gates, which are particularly problematic, but every known solution compromises security, so people have been very hesitant to actually deploy those. So nobody actually does table reuse as far as I know.
So in this you are encrypting a function, where in the previous one you are encrypting the data.
It's both. Well, you can see which function you're evaluating because you can view the netlist, but every one of these gates is kind of like, you can think of it as like a little puzzle. And then the inputs are also encrypted, and those are kind of like the keys to unlocking the puzzle. So it's actually literally a 4-entry lookup table, truth table, and only one of them will decrypt correctly, depending on the input. So the inputs are like your keys, and you have a 2-input Boolean gate, 2 to 4, you can just find the unique row that it's supposed to get, and that's how you get your output, and then that becomes your key for the next one. So that's why it's so expensive, because you're literally doing 2 to 4 decryptions per Boolean gate. It's not ideal, but huge potential. Okay, so we have our 2 primitives. Now, how do we actually do something interesting with them? This is typically what a private inference actually looks like. So you have your private data, remember from the previous slides, and then you have your standard neural architecture, convolution, ReLU, fully connected, whatever. And what we do is we take our linear transformations, the columns and the FCs, we map those to homomorphic encryption because we know that works quite well. And for the nonlinear functions of our network, we use ReLU. Those we're going to use garbled surveys for. And then remember, we have our 2 phases, the garbler and the evaluator. And these are, when we start, the 2 heavy-hitting operations, the actual garbling and the processing of the linear layers. And our philosophy is that this is sort of the way to go. You want to do these hybrid protocols, is what we call them, not just use homomorphic encryption or garbled circuits. You want to mix and match them like heterogeneous computing. And what that allows you to do is really leverage the strengths of each primitive while overcoming sort of the critical weaknesses of them. So for example, with homomorphic encryption, as most people use it today, you couldn't compute ReLU. So that's a problem, so you offset it with garbled circuit and leverage the strengths of both of them. And as we'll see, when you benchmark these things, they're really, really slow. They're like 5 to 6 orders of magnitude slower than a plain text inference. So in order to overcome that, you can't just build one accelerator and call it a day. You really need a full stack solution. And what we're proposing are things from the machine learning level. What we're actually finding is that models designed for efficient plain text inference do not translate well to private inference. And then we're doing end-to-end systems sort of optimizations in determining which operations run parallel, when you communicate, what you store, how you actually leverage arrival rates. And then, of course, at the end of the day, none of this is going to work without custom hardware. So we also have solutions there as well. So let's start with some machine learning. I know this is a bit different from some of the other talks, but I think some of the takeaways will be of interest to people. And some of this stuff is hit close to our home communities, so maybe it'll give you some perspective on those papers. So we had this paper in NeurIPS 2020 called CryptoNAS, and what we were showing is basically when you look at the online, the real delay of computation for private inference, most of it is actually coming from ReLU, not convolutions. Right? So if you think about running a CNN today in plain text, you never think twice about ReLU because it's like the most simple operation you could ever perform. But in private computing, it's at least 10,000x slower than the linear layers. And what this made us think about is develop this notion of a ReLU budget, which is that when you're designing neural networks, you're thinking about how to build networks for private inference, you don't want to think about flops. You don't want to necessarily immediately prune flops. You actually want to think about ReLUs and how you effectively allocate ReLUs to the network. And so now you might be thinking, at least this is what I thought when we got there, well, if we have ReLU budget and ReLUs are such a problem, why don't we just get rid of ReLUs, right? Why do we use ReLU in the first place? Why can't we use something else? So our goal was to try to replace ReLUs with a polynomial that has a low degree, because we don't want to add tons of computation computing a high-degree polynomial. That would also not be great. And we want competitive performance. We don't want to sacrifice accuracy. The whole point is to leverage these massive machine learning models that give you high accuracy. So we don't want to compromise that. And we tried a ton of things. We really wanted to drop and replace polynomials that would almost fit a ReLU, right? So if you had a polynomial and made it fit a ReLU, we thought, hey, machine learning is robust to approximation, maybe this will work pretty well. And if you look at those actual approximations that we did, like you plot them and compute the error between the polynomial approximation and the actual ReLU function, it looks great. It overlaps almost perfectly. And we also found that it would work for small data sets in shallow networks, but it never actually worked for deep networks. And when I say deep, I mean we couldn't really get it to work for ResNet 18. And we found that there's actually a fundamental problem here. And when you step back and think about it, it actually makes a lot of sense. As you have a nice approximation of ReLU, and that approximation holds as long as your values are within some range. So in the early layers of the network, everything stays nice and within this range. Eventually what happens is a few activations at some layer exceed that nice approximation range. And because you're using an x squared, x to the fourth polynomial, they start exploding. And then all bets are off. 1 or 2 layers after you get that first escaping activation, that large value propagates to all the other values, and it basically blows up your whole inference, and it turns into infinite in Python. So it doesn't work, and it's not bounded. Yeah?
Cannot you use like spline regression or something, like piecewise polynomials that you can?
You can use piecewise polynomials, but you can't use any conditionals. So you can't choose between which one you do. So you could have like 3 different versions of the approximation coming out, but you wouldn't be able to select. You can't do any conditioning on the input. Yeah.
How about normalizing the activation values so that you can?
I'm sorry?
How about normalizing the activation values?
Yeah.
Okay.
So we were really stubborn. Like this was a first year student. I was like, look, you're going to replace ReLU with x squared. This is a well-defined problem. It's a great starter problem. So we're like, okay, before we tried that, we tried this. We were like, these networks aren't working. We keep exploding. We're going to hold its hand every step of the way. So we're going to train this whole thing, state-of-the-art training. And then every single layer, we're going to train the conv plus the quad approximation. Get perfect error, minimize all the error, make it fit perfectly. Freeze those and just step and train every layer one at a time and sort of hold its hand through training until you get to the end and then do a little fine-tuning. That actually worked. We could almost do VGG 16, which we thought was great, but it never worked with ResNet because we still had exploding activations. Then we got into this normalization bounding problem. And we proposed this approx min-max, where you basically look at the min and max values of the distribution of output activations at each layer, and try to renormalize between -1 and 1. The problem there is it actually does work really well if you can inspect your data. But if you try to approximate those mins and max using just the training data, it still doesn't work. Because it either smushes it way too much, or one still gets by and ends up blowing up your values. And if you could inspect the data during inference, you might as well do ReLU.
So what you're saying is the profiling data is not sufficient?
Yeah, at least in our experience, yes. Yeah. So we tried it, it didn't work. So we actually wrote up this paper called Sisyphus as a negative result and published it in PPML. So it was interesting. It's gotten a lot of spirited feedback. So I'd encourage you to read it. Like, we would love for someone to get it to work because that would solve a lot of problems in privacy preserving machine learning. But it's not as easy as drop and replace a polynomial function.
Brandon, you could have done it like batch normalization. So you could have estimated those parameters min and max at the batch level. Like batch normalization works like this, but it is like a standardization. So it subtracts the mean and divides by the standard deviation. So here you find the mean and max over a batch and do it at the batch level.
Yeah, and if you have, but you could do that, and if you have to inspect any of the live data though, you basically fall back to the same problem as having to do comparisons on the actual data. So if you can do it on the training data,
we are training. So that's why. So in batch normalization, they calculate these parameters at the training time.
right?
But they use the same parameters for the inference time. They do not recalculate it.
Right. So we could certainly try that, but for our experience, the training didn't quite match the eval or test perfectly. So we still had, we still had problems. But yeah, that would be a great thing to try out. We're not saying we exhaustively tried it. We're just saying you might want to think twice if you think you're going to solve it in a weekend. And we call this, because we always thought we solved it, and then the boulder rolled downhill and we started all over. Okay, so we didn't quite give up, but we asked a different question. We said, okay, well, we can't replace ReLU with x squared. Now, what if we just don't compute ReLUs? Because x squared just seems to be making everything worse. And this was a paper called DeepReduce, published in ICML 2021. And it works kind of like weight pruning, right? Basically, what we look for are actual full layers of ReLUs that we can knock out. And by knock out, because it's ReLU, it basically means linearizing it. So you just don't do any activation function for that layer. And we have a couple different techniques. We have this thing called culling, where if you're familiar with the ResNet architecture, it's blocked into stages. So you just literally knock out all the ReLUs in a certain stage. Thinning knocks out ReLUs in every other one, and then reshaping actually changes the tensor shape. We'll focus on culling for now because I think it's the most interesting. So we came up with this little equation for ReLU criticality, which is basically you inspect the network during training time to figure out which stages or layers of the network you think have the most critical ReLUs. And you normalize it by the number of ReLUs per stage. This is actually similar to how ENAS and Google has done some of their weight pruning techniques. And when you run it, you find some interesting results. Basically, all the different stages in things like ResNets, the ReLUs aren't all created equal. So you see a pretty skewed distribution of criticality among the networks. We don't have a theoretical proof of this or anything, but we consistently found that in ResNet and CNN-based architectures, the early stages of the networks had less critical ReLUs. And this is actually pretty interesting because if you look at a breakdown of CNNs, right, where stuff happens, distributed by the layer down here, the number of parameters tends to increase with depth. The number of flops tends to stay pretty much equal. But the number of ReLUs, most of them actually happen early on in the early stages of the network. And if you overlay this with our criticality of ReLU stages, well, actually about 50% of ReLUs are happening in the first stage, which we just saw is super not critical. And the interesting thing is you can actually just drop all of those ReLUs from the network, basically linearizing the entire first stage of a CNN and lose almost no accuracy. We do a lot of knowledge distillation and some training tricks, but it does work really well. And this effectively allowed us to blow away all the existing state-of-the-art. With this technique, we got Pareto dominance across a very wide range of ReLUs and accuracy. So we got some impressive numbers. And what we found is that culling works really well for many ReLUs and high accuracy. And then if you want more aggressive performance, say at the expense of accuracy, thinning and actual model reshaping start to come in if you inspect those points along the Pareto frontier. And then if we look at the slowest, most accurate point here, we're able to run, this is a SciFar 100 inference in about 4.6 seconds, which is not bad on a CPU, so we're pretty happy about that.
So it is very complicated because they say that you use non-linear activations to increase the representation power of neural networks. If you have only linear activation, then it is equivalent to a single layer neural
Exactly.
network. So, and you are linearizing those layers. So
Exactly.
you are not, you must be losing on the accuracy of the network, the overall accuracy of the network.
Yeah, so I can't tell you why it's working, but I'm very confident it's working. We tried a lot of different things. So some people think it just helps with training. You train with everything in there, and then when you drop and then distill, that's easier. Because what we did is we actually tried to train smaller networks from scratch instead of starting with a big network and pruning it down. That didn't work as well. So that's basically these purple lines here.
But you're not linearizing all the values, only some values.
Yeah, we're very selective
Yeah.
using this deeper shape heuristic in how we're doing it.
And how much you're losing on the overall accuracy?
For the top point here, that's, I believe, pretty close to the baseline. So I'll have to check the papers, but it feels like competitive with the state of the art at the time for these size of models.
I don't know whether this is relevant, but I'm also working on like pruning side. But if I look at the level of important thing over there, it looks very similar to the sparsity degree per layer after the pruning, right? All the layers are going to be mostly dense, and then for the late layers, they will be very, very sparse. So the number of nodes.
So for your weight pruning, deeper layers are easier to prune?
Yeah.
Oh, that's actually, so we should talk about this follow-up, because one of the interesting takeaways that is undersold in this paper is that the point that's being made is a good one. When you knock out ReLUs, you can technically collapse them because they're two adjacent linear transformations. So what we're actually showed in DeepReduce in a buried table in there is that DeepReduce is actually competitive with channel pruning because we're able to save so many flops, even though that wasn't the objective we set out to do, because you can collapse so many of these layers. But we work really well at the front layers. So if you actually wanted to like do this together, that would probably work really well. We would blow away those first stage, basically collapse all that into one effectively transformation, and then you could apply this hardcore weight pruning on the latter layers, and you might be competitive with the state of the art. So we should follow up.
That's interesting.
On that. Yeah.
Just a quick question. Want to confirm with you, your model is actually trained with parallel layers, but when you prune it, it takes out parallel layers.
Yes. As I was explaining, very selectively. So the whole, well, DeepReduce did propose dropping ReLUs, but also exactly how you choose which ReLUs to drop, like in weight pruning, how you choose which weight you drop is really important.
So you are dropping it at the inference time, not at the training time.
At training time, you have all the ReLUs.
Okay.
Then DeepReduce tells you which ones we think would be okay to drop, and then when you actually would deploy the network, it doesn't have those ReLUs. Yep. Okay. So we just talked a lot about ReLU and machine learning, so let's bring it back to performance and systems, right? And the title of this talk and the point of my lab's research is not to build networks with the fewest amount of ReLUs, right? It's to enable real-time private inference. So does anything stick out here? So when we talked about performance here, there's one key word, and that's online. This is only considering the online runtime of these overheads, which is a little subtle and a little tricky. So to understand this, let's look at the actual performance of the end-to-end systems. And what we did here is we actually took those protocols, built them, ran them, profiled them, understood them, and then built a simulator so we could actually study this thing in a full end-to-end system, because these protocols are actually quite complex. And it's really hard to pin down exactly what's holding you back and where all the cycles are going. So we coded this thing up. We actually ran all the protocols, and we studied the system level costs using ResNet 18 on tiny ImageNet. And I think someone who's working on LLMs and a lot of other big models, but ResNet 18 is sort of pushing what we can reasonably work with today. So in the ML community, it's kind of state of the art for privacy preserving computation. And what we found was quite surprising. And this is not considering only the online phase. I'll explain this in a slide. This is the full offline and online. So the first thing is that the storage requirements per inference are effectively astronomical. So for a single inference on tiny ImageNet, you need 41 gigabytes of storage. The reason we're not evaluating ImageNet here, we actually did run it once to see what would happen. You need half a terabyte of storage for one inference. So this is like a non-starter, right? That's crazy. Think about how much storage your phone has. And you can't use all that for one inference. The second problem is compute. So when you actually look at these things, well, guess what? Well, sort of like lurking behind the scenes of all these protocols is homomorphic encryption. And homomorphic encryption, as we all know from old papers, is very, very slow. On a CPU, using a state-of-the-art software implementation, that takes about 18 minutes just to run the homomorphic encryption. And finally, there's the communication. So you do have to communicate all these tables for the garbled circuit back and forth. And even if you're using state-of-the-art 5G optimistic wireless bandwidth, it's going to take you about 11 minutes to communicate what you need to communicate for a single inference. And so the question is, some folks are reporting really fast latencies, like we did in DeepReduce. We said, oh, you can do one in 4 seconds. This data doesn't match what's going on. So there's something neat you can do here if you recall our protocol, right? You have linear transformations in homomorphic encryption, nonlinears in ReLU that has 2 phases. Well, it turns out that the homomorphic encryption and the server garbling actually aren't dependent on any actual input data. So they only use sort of like constants or randomly generated data, and what folks do is they move them to an offline phase. So they assume there's some time before time where all of this stuff can happen behind the scenes, and we don't have to pay for it when we want to do our actual inference. So when your data actually arrives to the cloud encrypted, you only have to do this evaluation, the garbled circuit evaluator, and we do have to introduce this new protocol called secret sharing, but you can effectively assume that's free. It's basically like doing a plain text calculation. But it depends on these things happening before. And so what's going on here is that this client storage and communication of 41 gigabytes per inference is not being counted because we're assuming it's offline. And this basically a half an hour's worth of computation time is also not being counted. And then we get to report latencies of like 4 minutes of online time, because that's all you would see. The problem is that that doesn't actually work when you want to do more than one inference, right? So if you just wanted to do one inference, which is what prior work did, and these are really great papers like Gazelle and Delphi, published at top security and privacy venues, then you can actually hide those costs, right? You can store 40 gigabytes, and you can spend a half an hour to compute one thing, but that's not how most machine learning systems work. We don't run one inference, we run hundreds. We support rates of arrival. We want to run multiple inferences per hour, per second, whatever your metric is. And what happens is that as you start increasing your rate of arrival, these pre-processing or offline costs start to come online. You can't mask them. Think about hiding latency in like a pipeline or something like that. Your arrival rate is increasing too much. You have to start paying that offline cost online. And then as you get to like one request every hour, not only are you paying the offline cost, you're actually starting to queue up inferences because you're processing them too slow, to the point where even at one request every 30 minutes, you're taking about an hour of effectively paid time to process them. And so you're sort of, it cuts both ways. Either you run out of storage, so if you have infinite compute, and you could just compute these pre-processing phases instantly, you still couldn't store them. Or if you had infinite storage, the compute is so slow, you wouldn't be able to process them in time. So you need to solve both of these problems.
So the question that you said that these things can be done offline because they are data independent. Now, why they cannot be used again for new samples? Why there is a cause?
So it's data independent, but like the randomness you use to do each pre-computation can't be reused. So you have to have a new sample every single time.
So every single time you have to spend about 29 minutes.
Yeah. Yep.
So then what's the advantage of doing it offline if you have to?
Oh, because like imagine that I had a medical image, or like you and I were going to do something, we were only going to compute one inference per day. Then say when we go to bed, we could do the pre-compute, we could store it, and then whenever you're ready to do that private inference, then you could use those pre-computes and only pay the online time. So if you had time to hide that pre-compute latency and storage to store it, you wouldn't have to pay it when you wanted to make your inference. Yeah?
So even if you have infinite compute and storage, if you can parallelize enough for the pre-processing phase, then you cannot hide the latency.
If you have infinite, yeah. If you have infinite storage or you have infinite compute, then you're okay. But yeah, what we're showing is that a lot of the results saying like second, on the order of a second per inference are sort of masking these huge costs that are sort of lurking under the rug. But you need both. That's the other thing. And if you think about how much storage your smartphone has, you're not going to be able to have gigabytes per inference. Okay, so what can we do about this, right? So if we look at our heavy hitters, the first one we said was this garbler, this garbled circuit garbler phase. So what happens here is that all these protocols assume that the server is the garbler, and then they send these tables over to the client who's going to act as the evaluator, right? But that doesn't really make sense for our setup because the client is usually a smartphone or even a laptop, right? Whereas we assume that the server would have access to much more storage. So if you look at the security guarantees of garbled circuits, they're actually symmetrical or symmetric. So what you can do is just flip the roles of the garbler and the evaluator. So that's what we do. We propose to have the client be the garbler and then send those tables to the server, and then the server store them and then use them as it happens. And this turns out to work quite well. We can basically buffer 5 times more pre-computes per client-server pair. That might seem a bit simple. We just like reversed the parties and got some nice little speed up. It is, but you also don't see these things until you look at the end-to-end problem. And there's also a lot of implications, which is why the original authors proposed the protocol in this way. So when you reverse the roles, you do have to bring some of that offline work online, so there is more of a cost. The allocation of bandwidth, you actually need more upload bandwidth now than download bandwidth. And if you look at the way that a lot of networks are provisioned, usually the download link is much more faster, has more bandwidth than the upload link. Interestingly, another part of this paper that we're not going to present today, in the 5G protocol, you can actually configure how you allocate bandwidth. It's actually part of the 5G standard, so you can get around that problem. And then the actual computation of the GC is swapped. So now you're actually putting more pressure on the client. The garbler is a little more expensive to compute, so you do add a bit of latency. But despite that, this ends up being a net overall win. So now we sort of addressed the garbled circuit part of things. What about the homomorphic encryption in that massive runtime? Well, if we look at our standard setup here, basically what we're doing is you're transforming a random sample through the weight matrix. So that's what's actually being evaluated here. You're not doing the actual input, it's just some randomness, and that allows the protocol to work out correctly. And this is what allowed prior work to move the homomorphic encryption to the offline phase, because the HE computations didn't depend on the user data, just some random generated data before time. Well, what's interesting is that when you actually dig into, this is the full protocol here, what's going on, the homomorphic encryption computation isn't just independent from the user data. Actually, every layer of homomorphic encryption computation is also independent. So what that means is that if you think about your standard neural architecture, right, the layer dependence, like from one layer to the next, you can actually break that and run all of your HE layers in parallel. So this is like embarrassing parallelism across layers of a neural network. And the really cool, I mean, this works really well. We get basically 10x speed up in software. It's super easy to implement because you're literally just parallelizing layers of homomorphic encryption. The other cool thing is this is generally applicable, so all prior homomorphic encryption accelerators, Cheetah, F1, Cradle Lake, BTS, they could all leverage this and effectively get a factor of speed up proportional to the number of layers of the network to sort of close that remaining gap. if you were willing to pay the cost. So yeah, we hooked this up, we evaluated it. So this is the baseline protocol published in this top security conferences. The blue line's us. We get much better latency. We reduce it end-to-end by about 2x. We sustain a much higher throughput. The problem is the observed latency is still incredibly high, so you can see the y-axis is still labeled in minutes. And then even though we were able to push out the arrival rates that we're able to sustain in the system, we're still only able to handle like one request every 15 minutes. So there's still quite a ways to go. If you'd like to learn more, this paper was published at FastPath2023. We presented it a couple weeks ago up in Canada. We also released all the code. So if you actually want to get involved with this line of research, you can check out Karthik's GitHub repo. He calls it Kryptonite. See how things run, see where the bottlenecks are, and then if you have like an accelerator or some optimization, you're able to knock out some ReLUs or prune a network really cleverly, you can just plug it in here and get the new runtime of your system. And now we have some nice Amdahl's law, Amdahl's type analysis of where time is going. Okay, so I'm about at time. I'll just go through the last few things kind of quickly. So we talked about how we can optimize machine learning. We talked about some of the systems challenges, what we can do there. But ultimately, at the end of the day, you are going to need custom hardware to overcome these costs. So the first thing that we've done is develop a homomorphic encryption accelerator. This is actually going to be published at ISPAS on Tuesday by my student Nigar. So I won't steal her thunder, but you should all go check out the talk. But it's sort of like the same thing. If you dig into homomorphic encryption and you look at what the challenges are, we say that there's 3. The first one is that each computation of a cheat involves a large word modular computation. You have to do computation into the field. This is not something that computers today excel at. It's tough. The second one is that when you do a computation, like a multiply, a plain text multiply in ciphertext, you're not just doing a multiply. The actual multiply is actually the easy part. Then there's all these sort of meta bookkeeping functions you have to run after you do the multiply that just add an incredible amount of extra work per function. So you have a lot more work to do. And third, you have large data structures. But if you look at each of these workloads, it actually looks like it would work quite well with vectors. And when I say vector, I mean like a classic vector ISA, like the old school Cray supercomputers. So what we're setting out to do is say, well, we're building all these fixed function accelerators. Why not build a old school supercomputer tailored to homomorphic encryption? So we basically propose a new vector ISA, we call it B512, that has 512 linked vectors. It only has 17 to 20 instructions, and then it just has fixed function support for all of those large word modular computations and a couple special instructions to process things like NTTs, which are basically FFTs, really well. And then we have a really super simple front end. And then we, because this is data oblivious, push everything up to the compiler and have the compiler schedule all the code onto the machine. And the reason for this is work that's funded through the DARPA DeepRive program, is that a lot of people don't want fixed function hardware for homomorphic encryption. They want more general programmable solutions because all of this stuff is still evolving, right? It hasn't even been around that long. New homomorphic encryption schemes are getting developed all the time. We're seeing the same sorts of computations being used in PQC. So yeah, we thought vectors would be a nice way to solve the problem, and you can come check out the full talk on Tuesday. Okay, and I have 1 minute, so I'll just tease Cambridge's paper here. So yeah, the other thing we did is we built a hardware accelerator for garbled circuits. We call it HACK. And this is work that'll appear at ISCA 2023. My student Jen Chow led this effort. So yeah, basically we're going back to the future. We did vectors for homomorphic encryption, And for garbled circuits, we're doing VLIW. And if you think about it, why didn't VLIW work? There's lots of reasons VLIW didn't work, and it's not true VLIW, it's VLIW inspired. All of those we don't have in garbled circuits because everything is completely data oblivious. So what we do is we build pretty deep, rigid, in-order pipelines to handle like the core computations in the garbled circuit, and then we push all of the scheduling of work and parallelization up to the compiler. We actually do have a full functional and optimizing compiler to schedule and program this thing and handle all the data movement. And because it's data oblivious, you basically know every dependence, every memory access, and every delay at compile time. So as long as you have a pretty intelligent compiler, it can schedule this thing. And it turns out that works pretty well. So using just 4.3 millimeters squared in TSMC 16, we get about 2 to 3 orders of magnitude speed up, depending on which memory technology we use here. Compared to plain text, we have a slowdown of only 75x. And if you remove this one benchmark, we use VIP bench, the privacy benchmark suite, if anyone's heard of that, to evaluate this. Then we're within 23x. And the reason gradient descent is so slow is it actually uses true floating point. So when we do garbled circuits, we don't approximate. It's not fixed point, it's actual floating point circuits. So if you want that, we can give it to you. And it's so slow because x86 has a floating point instruction. So x86 works really well for Intel, but when you boil it down to a Boolean netlist and run it through a garbled circuit, the floating point circuit is huge, right? So even with an accelerator, it's really slow, but if you ever want a floating point, we can do it. Yeah, so that's what we do. Links to the papers if you want more details. I think I'll leave you with this. I think we've been looking at PPCs for about 4 years now, homomorphic encryption and garbled circuits. I think they're super expensive, and they're going to cost a ton of energy and area to compute efficiently. But I think they're not fundamentally slow. If you actually inspect the workloads, they're first of all highly amenable to hardware acceleration, and they're extremely amenable to large-scale parallelization. So as long as you do build a big chip and program that chip properly, I think you can eat away at most of those overheads. But co-design is going to be key. Striking that right balance between the compiler and the hardware is at least what we think is going to make all of this possible. So that's all I have. I think I'm actually pretty close to being on time, so I'll call it there. Thank you all for sticking around until the very end here. I'm happy to take any questions.
Thank you.
Thanks.
I'll ask you a question. And so there's some domain-specific PPC sort of techniques, like for SQL sort of stuff, not all of SQL, but important subsets of it, where you can get like 90% of plain text speed with very little hardware overhead. I think ridge regression, which is a variation of linear regression, is another one where you can do that sort of. I mean, you're focusing on the general problem, not those specific ones, but I just wondered if you have any view on how well specific techniques might come up in important domains that would address the PPC issue.
So I think like anything sort of linear regression based should work pretty well with this stuff we have here, but like with the information retrieval or querying a database or anything like that, any sort of ability, like if you think about it, basically one person's going to get his PhD in removing RALUs from a network because there's so much benefit to that. So if there's an equivalent of that domain optimization to SQL that you can do based on the constraints of the PPC, I think that's where you'll see a big one. I don't know enough about that particular one to say what that is, but I know a lot of people are very interested in it.
Yeah, sorry, I don't remember the exact reference. There's an MIT paper a few years ago on the SQL one. Is it Berkeley? I can't remember.
Okay. If they're doing homomorphic encryption.
No, they're not.
Oh.
No homomorphic. Just they're sort of domain experts in this area, and they look at it and say, we can do this privately for this subset of computation because we know, I don't understand SQL particularly what the techniques are, but they don't need to use FAG or garbled circuits or anything.
I see. Yeah, if you can avoid using, so we're only looking at applying these techniques. If you can avoid using them, you're going to save 5 orders of magnitude right off the bat. Yeah.
I have one question.
Yeah.
So you said that you can break down the layer because of the layer structure of the neural networks. For each layer, you can calculate that in parallel, right? Calculating. So my question, and then it is data independent, right?
Yes.
Yes. So my question is that can you not pre-compute for each layer multiple such representations, and then just pick some permutations of those during the to create end-to-end network for different samples or different images?
So you want to pre-compute a bunch of different ones
For each layer.
For each layer.
And then just combine them, permutation of them, take them, because they are also independent from each other, right?
Yeah.
So you could, for each sample, you can just pick a combination of them, and you
For the actual data sample.
yes.
Yeah, so that's what you do.
No, I'm saying that you don't have to compute. You can just pre-compute for each layer multiple such whatever representations that you need.
And depending on the data, you can
Independent of the data, pre-compute, and when you have to do inference, you can take a combination of them, one from here, and make it.
if I'm understanding correctly, I think that's what happens.
Okay.
Yeah. Like you do all these pre-computes of all the layers.
No, but for each layer you pre-compute multiple because you said that you have to do it again because
Yeah.
So that you can pre-compute, right?
Yes. Yep.
So then when you have a sample, you can say you have 100 for representations for one layer, 100 for other, 100 for other. You can choose 100, choose one, and times 100, choose one time. It cannot work like that.
Oh, I see. Oh, that's interesting. I see what you're saying. Yeah, that's an interesting question. I'm not sure. That's a security question, so I don't want to give an answer, but that's an interesting idea. Yeah, I see what you're saying. We should evaluate that. We try not to, once you start touching security, you open up a new can of worms of like, is this secure? Is it not secure? And if it is secure, please prove it. So we try to take the protocols and then speed them up. But this is a really interesting idea. Yeah, it's a good question. We had something similar with the ReLU, because ReLUs and a layer are all independent.
Yeah.
So obviously, if you decrypted the whole layer in order, you could learn something about the data. If you randomly shuffled it around and gave it and decrypted it, maybe you couldn't figure it out. Yeah, because then you just shuffle the weight matrix to match the shuffle of ReLUs and everything would work out. But yeah, reviewers didn't like that.
Okay, well,
Right.
very good
Thanks, everyone.
stuff. Good luck. Thank you. And stay tuned on Tuesday. And it is.
This is yours. Oh, thank you.
Well, yeah, I will give it.
And then,
This I will give it to.
Okay. Thank you.
If you have any closing words, but I'll just say, thank you all for attending. You know, really good questions, lots of conversation, ideas, and so forth. So I think it's a successful workshop in addition to terrific speakers. So thank you all for coming.
Yeah, hopefully you will get involved for next year's workshop also, right? In some capacity, you almost are going to contribute.
Absolutely.
Thank you, everyone.
Thank you.
Thanks, Brandon.
Thank you. Thanks for all the questions.